is going on, man? Okay, it turns out we're already 10 past. I didn't notice with the previous class taking longer. So welcome back. This is going to be longer than what's advertised on the website. So we're going to have multiple lectures, kind of, in machine learning. So I said today was going to be supervised learning, and I know this is kind of not exactly the proper way to cut these concepts, but it's close enough. And I think the dates, the website is actually last year's lecture. That's going to be also updated before I upload these slides. And half of the lecture will be given by Forrest Iandola, who's an expert on scaling deep learning. He's probably one of the world's foremost experts. I'll first give an overview about the machine learning lectures, both today and Thursday's lectures, and what the contents will be. I'll give a little bit of brief introduction about concepts, methods, so that, and parallelization attempts. Hope to get you on the same page and avoid future confusion. Talk very briefly on neural networks and hand it over to Forrest, and then I'll conclude with support vector machines, which is another supervised learning technique. So this is the longer outline. Today we're hoping to do what I just told you, and Thursday I will eat about half of the graph partitioning lectures, which is becoming slightly less interesting for students as time goes on. Everyone probably needs to learn what graph partitioning is, but not everyone needs to know all the 10 different algorithms that take it. At some point it becomes a little too much detail, so we're going to cut it short this year. And we'll see instead a couple of other methods, matrix factorizations, different clustering methods, and some graphical model estimation, also known as inverse covariance matrix estimation. So this is a nice diagram of different machine learning methodologies, but before that, a good definition of machine learning seems to be lacking, but a good way to define it is by considering what kind of a question machine learning is trying to answer. It's about really building computer systems that automate and automatically improve its experience. How do we build those systems, and what are the fundamental laws? Meaning that when we are working on computer automated learning, what are the limits? And so there are two questions here, right? Both algorithmic and systems building. Machine learning concerns both of them. So a common confusion I see is, at first, when you look at a vast literature, perhaps not a big problem for a lot of students that are enrolled. I've looked at the homework zeros and looked like half of them was invariance of machine learning, at least, maybe not more. So maybe I'm lecturing maybe for the other half, we'll see. The main confusion seems to stem from specific learning methods and learning tasks. So the task is dimensionality reduction. You have a data set, for example, that has apparently millions of features when you directly observe them, but you know that they're supposed to be lying on a smaller, lower dimensional space. And you're trying to recover what that lower dimensional space is from that raw feature set. And that's dimensionality reduction. There are methods. Principal component analysis used to be one of the most popular, and perhaps still in sciences that's the case. And we'll see one of them on Thursday, which is non-negative matrix factorization, which is another dimensionality reduction methodology. And then you have a supervised learning classification task, for example, or a regression task. You try to classify objects, the standard, what you read in the news, based on their feature sets, and support vector machine is one of the methods. And the second one is a little more subtle, is the optimization technique to solve the problem, for example, training neural networks. So stochastic gradient descent is perhaps the most popular algorithm, but you can use stochastic gradient descent to solve a lot of other problems. You can do matrix factorization with it. You can solve even support vector machines, in fact. Whether or not it's the right algorithm to do so is a different question. But essentially, stochastic gradient descent is just a first order optimization algorithm. As long as your problem looks like some optimization function, you can apply it. But for specific systems like, for example, support vector machines, there are specialized algorithms, and we're going to see a little bit about it, called sequential minimal optimization, for example. They might be better suited than black box stochastic gradient descent. And the CS267's standard picture that probably repeatedly comes up is what kind of so-called computational motifs map to what applications. And here I'm highlighting the machine learning column. ML stands for machine learning. And we see that there are connections to graph algorithms, dense matrices, sparse matrices, dynamic programming, graphical models, and backtracking and branch and bound. These are heavily reliant on those. And then there's medium scale reliance on spectral methods such as FFT, finite state machines, and unstructured grids. And of course, we said there's a heavy reliance on dense and sparse matrix methods. Here is one way to actually illustrate it in specific tasks. So what we're here on top is different machine learning tasks. I color-coded the supervised learning task with green, and the orange ones are unsupervised learning tasks. And this is somewhat of a loose dependency diagram as a bipartite graph. Just let's pick one of those. For example, let's say you want to do dimensionality reduction, which is one of the richest ones. It relies on a lot of linear algebra primitives. And some algorithms use only 2 of them, some of them use only 1 of them. But at the end of the day, they have a significant dependence on a bunch of linear algebra operations, what we call usually BLAS operations. For basic linear algebra subroutines, you've seen this in the dense linear algebra class, but there is a sparse BLAS, and there's even something called a graph BLAS, which is a sparse BLAS with a slightly more flexible interface. And some actually more than slightly. And you can probably densify this plot, and keep in mind that this is, again, one way to do it. You can solve non-negative matrix factorization using 5 different algorithms. And this is one of my favorite distinctions, implicit parallelization and explicit parallelization. So implicit parallelization, you keep the overall algorithm structure, whatever the method's optimization algorithm, pretty much intact. And you try to parallelize individual components of them, like the previous slide. So if I come up with a parallel, let's say sparse matrix multiply, I will automatically get for example, a Markov clustering algorithm we'll talk about on Thursday, and it will be giving the exact result. Right? As long as my parallelization is faithful to the original algorithm, right? I'll get the same convergence properties and same results. And the deep neural network example is essentially model parallelism. So you will get the same convergence properties if you do model parallelism. And so you're not really changing the algorithm. The downside of this approach can be that if your algorithm has a long critical path, like a lot of steps involving these operations, either matrix operations or other building blocks, and you only parallelize the building blocks, your overall critical path might not shrink long enough. Right? If your outer loop is order n, and you only parallelize what's inside that loop, you will still have an order n dependency. So that depends on how much parallelism are in there in these individual operations. If there is enough, then this might be a possible opportunity. If not, you might need to consider what I consider as explicit parallelization. Here we're modifying the overall algorithm structure to extract more parallelism. And so we'll see an example on support vector machines where we actually train individual support vector machines and combine the results. The accuracy is different slightly, or in some algorithms significantly different. or data parallelism in deep neural networks, where you basically, instead of training one sample at a time, which is the stochastic gradient descent's standard form, you just, to extract more parallelism, you're training B batches at a time, so you get different behavior in practice, but you get more parallelism. So that's the one major difference. So let's go a little bit about neural networks, and I'll hand it over to Forrest. So what is training? Training is really just you're given, this is a neural network, the very shallow example I put just two because I got bored about drawing large ones. So what's going on? You have input features x1 and x2. You're trying to figure out an output feature y, right? And how can you minimize the training error is when your knobs here are your weights, right? You change wij's for all the weights you have in your network and trying to fit the correct classes you have in your training data. That's what you're doing. But how are you doing is the important part. The classical algorithm, I'm not saying stochastic gradient descent, the gradient descent is really, you go look at the loss function, so-called your error, and you try to follow the direction of the steepest descent. So you take the derivatives of your loss function and see how you can influence that as strongly as possible, and you follow the steepest direction on that, right? And again, this is the, and you decide the alpha, which is your learning rate. What does that mean? So you can take a big step and hopefully get closer to your result, but the problem is if it's outside your function's well-behaving region, you might be taking too much of a big step, and you might need to zigzag back. So that's the downside of you have to think about your step size and what is depending on your surface. Function surface. What is stochastic gradient descent? The previous algorithm needs to compute the derivatives with respect to all the samples. It needs to compute this gigantic matrix called Jacobian matrix, which is particularly expensive, and find out all the partial derivatives. Instead, the online faster way to do that is just to take one sample at a time, compute the partial derivatives with respect to that sample only, and then take a step, and then take another sample. And just keep doing it one after another. So naturally, people came up with versions that are in the middle, which is instead of taking one sample, you take B samples, and then you take a batched stochastic gradient descent step. And this has this sits somewhere in between the pure gradient descent and pure SGD. Those are beyond the scope of this lecture. I'm only talking about parallelism here, but I want to say something that the name is a little bit of a misnomer. The descent methods in the community, optimization community, are usually methods that always minimize some function. SGD doesn't have to minimize the function because you'll be only taking derivatives with respect to a single sample. It can be noisy. You might be following the wrong path a little bit. So you're basically, the loss function you're trying to minimize can look like up and down, going up and down. But this has also advantages. According to certain people, that if you're stuck in a local minima, this might help you get out of it by taking a slightly incorrect step, but that lets you get out of the local minima you just found yourself in. All right, so how do you compute the derivatives is an algorithm known as backpropagation. And all that I'm trying to say in the slide is this is a much deeper topic than just deep neural networks. How to calculate derivatives efficiently is topic of lots of books, and somehow the communities don't actually read each other's books. You can find these, the art of differentiating computer programs. Some people call this algorithmic differentiation, some people call it automatic differentiation. That didn't really help the visibility of the community either, because you can't Google doesn't even know to return the other result when you search it, which is somewhat sad. But know that backpropagation is a special case of automatic differentiation in reverse mode, and that's all I'm going to say here. So there are two types of parallelism when you're training neural networks using stochastic gradient descent, and And one of them is data parallelism. I said you take, instead of taking one sample at a time, you take B samples. This is more accurately called batch parallelism because there can be more parallelism in the data space, but we'll stick to the common terminology in the community for this lecture. So everyone basically updates the gradients somehow. So you have to let the other processors know how the gradients are changing. The old school approach, probably one of the first papers about this, which is no longer considered the state of the art, used a concept called a parameter server that keeps all the gradient information. And as everyone trains in their pieces of the data, they push the corrections to that parameter server. This can be this parameter server can be centralized, can be distributed, but it can be updated synchronously or asynchronously. Those are creating a huge variety of different algorithmic options that Forrest will talk about, hopefully. And again, I'm just going to skip it so that I give good enough time for Forrest to talk about these things. And as you can see, he was already in the slides before he agreed to come and give his portion. So one thing I want to say here is there is a little bit of a tendency to reinvent some of the algorithms that HPC and parallel computing has known. Avoid it if possible. The MPI all reduce is a primitive that I talked to you about that sums or finds the maximum in a vector that's distributed in every processor. So that comes up when you're trying to find these, synchronize the gradients in this data parallelism case. A lot of papers talk about new all reduce algorithms. That are not new because they're already implemented in MPI. So you look at the history of them a little bit before you come up with your own all-reduced algorithms. It's hard to beat what's out there because they can be proved to be optimal. You can beat it by constants, by one way or another. Okay, so one thing I want to say is in data parallelism, the model here is the network. The weights of the network is replicated on every processor. Right? So everyone gets a different sample, and the model is replicated. Why can this work? How does it even fit? It depends. Some models are too big, and you need a different approach. But a lot of models that are out there that people are training with and playing with are not big enough for this to be a problem. So that's how it works. Model parallelism, in contrast, basically splits the neural network into multiple machines. And then you have to coordinate when you're actually doing the training. You can't just independently train and arrive at some meaningful gradient that you can push to the server. You have to basically do some communication. And I'll show you how this can happen in matrix operations in a couple of slides. So here's potentially one matrix view of forward propagation. You basically are given a bunch of inputs to this layer. Think of the neural network input layer, and you're going to the next layers. And there's a bunch of connections in between. So those connections are represented in the W matrix, N by M. And then, and B is the number of samples you have, the batch size in your data parallel stochastic gradient descent, and with one multiplication, you'll basically go to the next layer. Right? So this is how you can represent it in matrix operations. I'm not saying this is the most efficient way to do it. Some backends implemented as matrix multiply, not all of them. I think cuDNN originally did, and I don't know if they do it anymore, but it's easier to conceptualize for me. One thing that you might see if you implement this as matrices and you're talking about some sort of data parallelism with given a fixed batch size, you're trying to only cut this dimension in data parallelism. So at some point you'll hit a wall, right? You don't have enough parallelism beyond B. That's why people have been in a race to increase B without hurting the convergence or the test error rates. But you can also see another issue when these little pieces each processor will have, when you cut this, is too small, your performance will start suffering because you're dealing with a tall skinny matrix. And if you remember homework 1, it's harder to get performance in significantly skewed matrices. Here's a complete matrix view of this process, not just forward propagation in data parallelism. So just what I was trying to describe, you cut the data matrix on the batch dimension column-wise. So you see the forward propagation doesn't require any communication. The back propagation is 2 steps. In 1 step, you basically calculate the gradient of the loss function with respect to the weights, and you also calculate the gradient of the loss function with respect to the input activations. And you can also represent them as matrix operations. You don't have to again, but you can. And this nicely illustrates you what's going on. So here, when you're calculating the loss with respect to the gradient, you have to do an all reduce. That's basically shouts it to you what you can, what needs to happen. A couple of questions: which matrices are replicated? It's pretty obvious that the weight matrix is replicated in this case. Everyone owns it. Where is the communication? It's only on the all reduce. And which steps can be overlapped? To me, it seems like there's a little bit of independence on. So the output here doesn't affect the other one, so you can do these 2 steps together. But not everything can be overlapped. And here's how to do the model parallelism in matrix notation. So what's the difference here? Instead of cutting the data matrix, I kept the data matrix replicated this time. I am cutting the weights matrix, the neural network itself. So now my forward propagation requires an all-getter, and now it requires communication. One of the back propagation steps became local, no need for communication, but I need to do an all reduce on the other step. So it seems to me that, I mean, there's an analysis, you can look at the papers, that this can win or lose depending on the relative ratio of the data in the data matrices compared to the model matrices. If your model matrix is really sparse or not a lot of variables, which is common in convolutional networks compared to fully connected networks that happen in, for example, recurrent neural networks. This is not a good idea in terms of communication. In the other cases, it can be. The other aspect also that's not highlighted here, and Forrest will come, is in the batch, in data parallelism, you get a performance boost by increasing the batch size because it doesn't affect the communication volume in general. But in model parallelism, it's there. You'll see that there's a factor B in your analysis. And that's about it. I'm not going to show how to merge them together because it's a little too convolved for me to explain in 1 minute, so I can hand over. But if you're interested, you can read the paper. So this is basically, and then I'll give you the other important piece. Don't worry about that. I can always push this. More proper introduction. Is this on? Oh, it is on. So first, Ion Dolla is now the CEO of DeepScale. Okay, and he used to be a grad student at UC Berkeley. Did some of the most groundbreaking work on scaling deep neural networks, and you can follow that in his Google Scholar page. And so you can probably tell a little bit about what DeepScale is doing, and feel free to advertise as much as you want.
Thanks for your introduction, and thanks for letting me speak. So before DeepScale, I did my PhD at Berkeley. Actually sat in this very room, in this class. So I took CS267 5 or so years ago, and then was a graduate student instructor for the class after that. And Jim was actually on my quals committee when I was doing my PhD. So really like this kind of work, and I think bridging the gap between HPC and machine learning has been some of the most interesting work I've done in my career so far. As I was wrapping up my PhD at Berkeley, I co-founded DeepScale with my former PhD advisor, Kirk Koitzer. We initially thought that we were going to commercialize, a sort of a cluster computer-oriented approach to scaling training. What we ultimately found is that it was an easier business model, and we could sort of make a bigger impact on a particular industry by selling the models themselves. So what we ended up doing, and what we do to this day, is to develop perception models, mainly computer vision models, to go in cars, both to make cars safer and to do collision avoidance technologies, as well as increasingly to enable autonomous vehicles. And we work with the auto industry, with automotive suppliers, with car companies on that. And I guess part of our unique angle is because we can train models very fast, we can more quickly discover very high quality deep neural net models that are worth putting into mass-produced vehicles. So Aydin gave a really nice sort of mathematical discussion of deep neural net training. I'm going to try my hand at giving a more intuitive discussion. And so basically, the arrows point right to left here to emphasize that this is for backpropagation. But first, you take an image, for example, that cat there, and you propagate it left to right through the network. So each layer's output becomes the next layer's input until you get to the end, and you have some sort of classification layer, the output of which is, hey, this hopefully does get classified as a cat, and if not, you go from right to left doing what's called backpropagation, fixing the mistakes that the model made that led to it incorrectly classifying this as not a cat. It also, as Aydin mentioned, typically you don't just do these one at a time. You often do these in a batch, which confusingly some people call it a batch or a mini batch. Those two terms actually mean the same thing. So you take a pile of images, you do this on all of them, and then you collect the updates to the model, the kind of summary of those mistakes in what are called gradients. So there are data gradients those are respect to the data, the input and output data of each layer, and then there are weight gradients, which are about how to update the weights or the parameters in the model. And the weight gradients then get added to the model after you complete this process. You do this over and over again, actually iterating through potentially millions of images repeatedly until you're satisfied with the accuracy level that the model is able to achieve. Also, I want to just kind of go over a little bit of terminologies I'm going to be using to try to minimize confusion. So deep neural nets and deep learning are more or less synonyms. They basically, deep neural nets and deep learning is a slightly more broad term. And then I think a term that's sort of picking up traction right now is more generically calling this field differentiable programming, where you may have any kind of multi-layer system that can use any sort of differentiable computer math to learn whatever concept you'd like to teach it. When I say training, I mean any mechanism for having a deep neural net learn from data. And given that this is the day that we're talking about supervised learning, we're talking mainly about using labeled data. So in the previous slide, you saw that we actually know that's a cat because someone wrote on that training image that we're looking at a cat. But for inference, which people sometimes call inference or deployment or scoring, that's where you're exercising the deep neural net on new data. And the whole point of having that deep neural net is so you can give it data that a human hasn't labeled, and the neural net can figure it out automatically. And then I guess I already mentioned a mini batch or a batch is a subset of a larger data set that you sort of train typically one batch at a time in the typical paradigms for deep neural net training. So in this talk, as well as in some of my own research, the focus really is to figure out how to train as fast as possible. So as of 2015, training the popular neural net called GoogleNet version 1 on what used to be a large data set, now we call it a medium-sized data set called ImageNet, took about 3 weeks. And this really stifled progress in terms of how quickly people could develop new deep neural nets. But worse, in practical and commercial applications, the data sets can be quite a bit larger. So, autonomous vehicles keep getting more and more sensors on them. So a typical autonomous vehicle prototype that you'll find here in the Bay Area or elsewhere will often have on the order of 8 cameras, as well as more advanced and exotic sensors like LiDAR, which is basically a laser scanner, as well as 1 or more radars. And this can easily gather gigabytes per second worth of data. And if you drive around for a day, you're looking at on the order of a petabyte worth of data. And even if you were to label a modest subset of the data that comes off these vehicles, you end up with a very, very large data set. And your training time, well, maybe isn't exactly proportional with your data set size, but certainly as you grow your data set, your training time tends to go up. Autonomous vehicles aren't the only place with this problem. So for example, seismic surveys for oil and gas routinely generate a petabyte of data. And so you end up with really large data volumes that you need to train on in order to get high accuracy. And I've heard many horror stories of people who say, well, I started this job and I looked at how long it was supposed to take to train and it was going to be over a year, right? And I think some of those jobs are probably still running, and some of them they said, okay, I'll Control-C that, I'll find some way to speed it up, or I'll go back to the drawing board. But training becomes one of the big bottlenecks to progress in deep neural networks. So one of the questions that we'll explore today is, given a large cluster or given kind of unlimited resources, what's the fastest approach to train a deep neural net on a large data set? And in my few minutes here, I won't claim to answer that question exhaustively, but I'll give you some ideas of what to think about when you're faced with this practical problem of scaling up training. So this is an area that I've been involved in as a researcher for quite a while, and I've been following for even longer. And I've seen sort of three communities within deep neural net land emerge with respect to scaling training. So most machine learning researchers actually don't scale their training, and I'll get to how they get any work done in a minute or two here. There's sort of the mathematical optimization community on the bottom right of this slide. And these folks tend to try to come up with really clever ways derived from the kind of things you'd see, for example, in the multi-geography level sort of distributed database type of work, right? So they're looking really at what can we do to manage fault tolerance? What clever math can we come up with to do asynchronous work? And often asynchronous parameter servers tend to be a dominant paradigm in that part of the research community. And then in the high performance computing community, which arguably this class has its roots in, what we tend to see is more emphasis on improving synchronous training, and I'll explain what that is in a bit. And as Aiden mentioned, Allreduce, which has been in the message passing interface, MPI standard for many, many years, is sort of a key workhorse to implementing that paradigm. So first of all, single GPU training. So a lot of folks kind of live a comfortable life in deep learning without scaling. So you might wonder how that's even possible. So even if you're working in deep learning for your career, you may not need large-scale training if you don't do a lot of original design of new deep neural net topologies or architectures. And if you're happy using deep neural nets that were pre-trained by others and just doing incremental training, so for example, a pretty high percentage of the papers that are published at the top computer vision and deep learning conferences like CVPR or NIPS, you'll find they basically downloaded someone else's deep neural net model that was already trained and made some improvements. Maybe they did a little bit of additional training on their data set, maybe they added some new layers or loss functions, but kind of started with that initial model. And so it's amazing how many people in industry and research don't design their own deep neural nets or train from scratch. As I'll get to later, if you do design your own deep neural nets, you can much more effectively control your own destiny in terms of what kind of computational footprints you'll need, what kind of hardware you can run on, and so forth. So there are many advantages to designing your own deep neural nets. Or perhaps you have just kind of small or mid-sized data sets that you can train in a more bounded amount of time on a single GPU or single workstation system. So there are a lot of folks happily living in this space. However, so I've seen lots of people say this, but one concrete example is Werner Vogels, who's the CTO of Amazon. He says that the ability to scale to multiple GPUs and specifically multiple hosts or multiple servers, and then to train larger models with larger and more sophisticated data sets. Deep learning models can take days or weeks to train, so even modest improvements can make a huge difference in the speed at which new models can be developed and evaluated. So those words are basically all things that I personally completely believe in and have experienced. And I think in the future of this community, both in research and in commercialization, we'll see more original deep neural net design. We'll see larger deep neural nets in terms of layers, model parameters, and any other dimensions that have yet to be invented. And then, of course, as we discussed before, larger data sets. So there are a lot of reasons to do distributed training, and I would argue that data sets are actually growing faster than Moore's law or any parallel version of Moore's law where hardware is getting better. So this is becoming a bigger and bigger issue. So again, as Aydin mentioned in his part of the talk, one of the paradigms that's been studied to do distributed training over more servers, typically more servers which each contain one or more GPUs, is what's called a parameter server. And so basically the top row there, the top box with those things in it, those are parameter servers. You can have one parameter server, you can have more than one. If you have more than one parameter server, then those parameter servers themselves have to have some protocol for sharing their updates. And then the middle row there is different, well, we'll call them training servers that each have a copy of the model in a data parallel or batch parallel approach to distributed training. And so whenever one of those training servers is ready with its new gradient updates, it just sends them to the parameter servers and then expects to hear a reply with, this is the latest gradients from more of the training servers. And this paper listed at the bottom is, I think was kind of one of the papers that set this community on fire. They talked a lot about using thousands of servers to do distributed training, and that was kind of really exciting. But when you start to dig into more of the numbers of this paper, and if you ask Jeff Dean, he'll typically agree with this, they hadn't spent a lot of time tuning the implementation on each server. So it wasn't kind of highly optimized, within 90% of peak, kind of super hyper efficient stuff. It was kind of best effort, some Java code in there somewhere, kind of scale out rather than prioritizing scale out over truly maximizing efficiency over the hardware that you have. And so the results that were presented in this paper, routinely got eaten by single box multi-GPU results after this. So it wasn't a highly efficient implementation. It was more of a cool idea with some impressive numbers of servers that they were just able to keep busy. But nevertheless, there were some interesting motivations for parameter servers, especially circa 2012. And it was sort of a simple programming model for machine learning in a distributed environment. And I use simple as a positive, a feature, not a bug. It was easy to reason about. Programmers could sort of treat a cluster like a supercomputer that could run thousands of computational threads. There were arguments in favor of the efficiency and the elastic scalability. And perhaps most interestingly, I think one of the things that parameter server approaches can do that other approaches still don't do great on is fault tolerance and durability. So if you're in an environment where there are a lot of hardware failures, or you're operating at a scale where just probabilistically a hardware failure at some point will happen, you don't have to face any downtime in your training. You just kind of continue. Whereas for the synchronous training that I'll get to later, typically you do have to go back to the most recent checkpoint if a piece of hardware fails. So one of the big problems with the parameter server approach is communication congestion. When I was at Berkeley, I was also a graduate student instructor for a class called CS194, which is ostensibly the undergrad version of CS267, but it also focuses more on sort of not just the algorithms, but also kind of parallel software architecture. And we have sort of similar to the set of dwarves or programming patterns that you find in parallel computing algorithms, we taught basically another set of patterns around sort of parallel software architecture. And one of the recurring types of software architecture in parallel computing that you find is sort of a centralized state repository. And this is something that basically is a pattern that you should look for and try to avoid. Because you almost always, at scale, end up with that central state repository being a bottleneck for the system as a whole. So some more empirical results on this. So these are as of 2016. Basically, what you'd expect is, so the y-axis is how long it took to train to converge to a certain level of accuracy on what was at the time a state-of-the-art deep neural net for computer vision. On the horizontal axis is how many GPUs we use for training. This was on the Oak Ridge Titan cluster, and it has basically 1 GPU per server, so number of GPUs equal the number of servers in these experiments. And what you'd expect to see is the more servers you throw at it up to some reasonable point, the less time it would take to train. What actually happens is it actually takes more time to train. And the big problem here was so the green part is the communication between servers, sending and receiving those gradient updates. And the blue part is the computation piece. And the more servers we had fighting over the parameter server to communicate, the more time we spent waiting around for those parameter servers to send and receive those updates. So that was pretty disappointing. So we dug into why, and in the paper, if you'd like to take a look at this paper, we do make some kind of more mathematical arguments around sort of runtimes and sort of very computer sciencey approach. There's also a more intuitive argument, and both of these are actually true. In the paper we talk about kind of kind of big O notation, how long does it take given some particular amount of bandwidth that you have at your disposal. But another piece of why this is slow is because there's quite low skew in mini-batch completion. So let's say you have 64 GPU servers that each take, let's say 32 images out of a larger batch size that's shared across all the servers. Often those servers all finish their work at about the same time. And they're all trying to talk to the parameter server or parameter servers at the same time. So 95% of mini-batch times are within 4% of the median. So that big spike there you see on that graph is basically when everybody's ready to start communicating. So low skew can lead to high contention. So again, basically all the training servers want to talk to the parameter server at about the same time, and it leads to a lot of congestion.
Can we just insert some random noise?
Yeah, so one approach you could take is to try to create some offsets between the servers, the training servers, and we tried that, and it did help to some degree. The next problem you hit is, let me go over this at the end. There's sort of a more mathy argument as well to how these are different. But yeah, basically, if you were to have a time slider on this, I would say kind of the single GPU training stuff was most popular, in the early days of deep learning. There's still a lot of people who do single GPU. More and more people have moved to distributed training. And I would say the asynchronous parameter server was kind of in its heyday from, let's call it 2012 to 2015. And then we and other HPC people figured this out at a similar time. So there's also a Baidu paper along with the FireCafe paper that came out around the same time with a similar idea. But we really saw the opportunity to use sort of the high performance computing concept of asynchronous all-reduce to really improve the efficiency of this problem. So basically, synchronous distributed deep neural net training with all-reduce, you distribute one mini batch over all your workers or training servers. And then one super step or one step in your training is where you have each training server locally update its gradients with the subset of those images it's been given, and then you perform an all-reduce over the network fabric in your data center across the different servers to update your gradients. So from this perspective, low skew is actually a big feature and not a bug. So what you need to be able to do this kind of collective all-reduce communication is for everybody to be ready to communicate at the same time. So if this was a high skew situation, all-reduce would actually not be a very good idea because you have a lot of servers just idling, waiting for that communication barrier to hit. But this low skew thing is actually a big benefit. It's what you want to see when considering doing a synchronous event like an all-reduce. And this actually looks a lot better. So basically, communication, doesn't end up being the dominant factor until you get to sort of well, this goes to 128. If you get to 256 GPUs, it started to dominate in our experience. But even at 128 GPUs, running at pretty good efficiency on each GPU and doing good utilization of the network interconnect between GPUs, we still end up with only about 30% of the runtime being in the communication piece. And this is in this paper, we basically didn't do any attempt to overlap the communication and computation. So there are certainly aspects of the communication that you could implement such that you're still working on, say, part of the backward pass and communicating what you've already finished. And you'd be able to get some overlap and maybe get some of that 30% to have communication and computation happening simultaneously. And more recently, there are a number of papers that have implemented that, and it's worked just as the math would predict. So putting it all together into sort of an application level evaluation, our experience with this was that, so first of all, we trained models like GoogleNet and found that we went from like 3 weeks to 10.5 hours. So that was about a 47 times speed up when running on 128 GPUs. Using the synchronous approach that I just described. One frustrating thing was when we went to 256 GPUs, the speed up started to kind of flatten out. So we got about a 60x speed up on 256 GPUs, which is still about 8.5 hours of training. And so this led us to start thinking about, could we rethink the topology or architecture of the neural network itself to require less communication? And so the communication in this sort of batch parallel or data parallel training approach, the amount that you communicate is actually equal to the number of parameters or the size of the parameters in the model. So GoogleNet version 1 had about 53 megabytes of parameters. We ended up doing some design space exploration, hunting around for new neural net designs that we could come up with, which actually is something that we did really, really fast because we could train so fast. And you wake up the next morning and you know how your models are doing. And so it was actually within a month or two of publishing the FireCafe paper that we discovered a family of neural nets called FireNets, of which our popular model SqueezeNet is an instance. This version of FireNet here is sort of a big SqueezeNet, you might call it. So this version has 13 megabytes of parameters, and it had similar accuracy, I think comparable accuracy to GoogleNet version 1, but given that it had fewer parameters, so only 13 megabytes instead of 53 megabytes, its scaling properties were much nicer. And so we were able to scale all the way to 256 GPUs and get 145x speed up on that. And we were able to train that model in about 3 hours. And this is kind of how life was for us in our heyday of doing distributed training research. We would really, go out for lunch and come back and really find out how our neural nets were doing, which is something that the single GPU, kind of comfy but lazy folks didn't have the luxury of being able to do. So these results, I know I present them enthusiastically, and I really enjoyed doing this work. This is actually from 2 to 3 years ago at this point. So the research community has moved very fast since then. And so on the left, this is FireCafe. This is really one of a couple papers that really popularized this switch from asynchronous parameter servers to synchronous all-reduce-based training. And today, if you download TensorFlow or other popular deep neural net frameworks or software packages, you'll find that most of them actually come off the shelf with both of the things that I'm most proud of doing in grad school. The SqueezeNet deep neural net model comes standard with most of these, and the synchronous all-reduced distributed training paradigm comes out of the box with most deep neural net frameworks today. So since the FireCafe work, there's been sort of a series of big improvements, and I don't have time to go into what exactly the tricks were for each of these papers to make things work better. But Google and Amazon and Facebook have all pushed things forward quite a bit, sort of from hours down to kind of close to being minutes. And actually, one of the most recent papers on this comes out of Berkeley from Jim Demmel's group, in fact. So Yang Yu is one of the grad students in Jim Demmel's group who led this work. And in the next slide, I'll actually show the citation for this one all the way on the right. But basically, they can train ResNet 50, which is actually more accurate than GoogleNet V1 in just 31 minutes. Using a cluster of CPUs, I believe, up at LBNL, and they also have some results on GPUs and Intel Xeon Phi chips as well. So I think we're now at a point where kind of lots of people know how to do distributed training, and now it's like, how do we improve it, scale it to the latest hardware, and come up with new tricks to make it way better. So So the one thing that I promised Aiden I would do is to also talk about, like, besides the skew thing, what else is different between sort of all-reduce and parameter servers. So let me go to that, and then I'll get to conclusions. So basically, in the traditional pre-reduction tree or pre-all-reduce sort of approach, the parameter servers basically had the following not so pleasant property, which is that, so let's say this is one parameter server, and this is a group of nodes that all report to this parameter server. Well, a network card, typically, when talking to one other server, gets completely saturated. So let's say you and I can talk at X number of gigabytes per second, right? And so I have a network card, you have a network card. My network card is completely tapped out just talking to you. So when there's one parameter server that has to receive and send updates to several other servers, it's basically a serial process. So of these 6 servers that are hooked up to this parameter server, each of those basically goes one at a time. And that just doesn't scale very nicely. And so even if you create kind of a bank of parameter servers that then communicate with each other, you're still in a situation where you end up basically needing lots of parameter servers per training server, and you're still stuck with the problem: how do those parameter servers then aggregate their updates? So all-reduce can be implemented in a few different ways. So there's a ring-based implementation, there's a reduction tree-based implementation, there are other approaches as well, Butterfly, for example. But one that's kind of easy to reason about mathematically and that does pretty well is a reduction tree. So each of these dots on the right-hand side of this slide are sort of hybrid communication, sort of, you think of each server as for communication and doing training, right? So every one of these servers does some training and then also receives gradient updates from 2 other servers and passes it to one server. So the nice thing about this approach is you don't have any one server that everybody's just waiting on. And those network cards are all utilized well, but not sort of the bottleneck anymore. So that's sort of a slightly more theoretical argument. So basically, first, if you have that nice skew property where everybody's done it at the same time, then you can move over to this reduction tree approach, and then you get these additional benefits. I think in the early work, with Google and Jeff Dean and so forth, those folks had spent so much time with these sort of unpredictable workloads with lots of distributed databases, lots of web queries that can come in at any time, and so they weren't used to living in a world where you have this nice predictable skew pattern. And so I think they just didn't think to push too hard on the all-reduce approach. So okay, let me start to wrap up here. So in the last few years, we've seen great progress on scaling training. Deep neural net training has gone from hours to weeks to minutes on what we used to consider to be large data sets, and then admittedly back up to hours and weeks again as we start to grow the data sets and the deep neural net architectures. But there's always sort of a squeeze and an expand portion to some folks really pounding on bigger data sets, bigger models, higher accuracy, and then some other folks figuring out how to make that all more efficiently usable. Naturally, further speed gains will be needed for larger data sets, which come from autonomous driving, medical imaging, and many other fields. Larger images and more types of sensors will also necessitate the ability to further accelerate the training of deep neural networks. And then there are certainly a lot of opportunities for speed improvements on the horizon that we haven't fully utilized as a community yet. So in terms of, as I didn't mention in the previous part of the talk, coming up with ways to make neural nets still converge and make fast progress in training, even at larger batch sizes, can lead to more parallelism being exposed in the system. And I should say, back in my day when I was doing the FireCafe stuff, basically if you went above like a batch size of 1024, maybe if you push your luck 2048, you'd either have the training not make that much progress per image that you go through, or it may even diverge. But there have been a lot of cool math tricks that have made that sort of large batch size much more feasible and productive today, and I think that's going to improve further. In fact, that's where this Yang Yu paper comes in, for example. There are a few others on this topic as well. I also think, while we've sort of pulled together the HPC community and the machine learning community, there's still more kind of interdisciplinary work to be done. So I think if we can get people who are designing the hardware, both at kind of a micro level and a data center level, and people who are designing the software and the implementations, and the people who are developing the deep neural net architectures themselves, if we can have those folks work more closely together, we'll have kind of, each of those groups will find a 10x speed up that only works with the other group's 10x speed up when you combine them for 100x speed up. So I think there are a lot of opportunities there that we haven't exploited yet as a community. And then finally, I think combining multiple types of parallelism. So doing, for example, model, batch, and domain or sub-image level parallelism. There are people who have worked on each of these things. I think figuring out how to effectively unify them, which admittedly will take a lot more lines of code to do well than doing only one of those at any given time. But if we can effectively unify those, there's an opportunity for doing the sort of kind of min cut along all dimensions of the algorithm. So I'll leave it there, and I'm happy to take a couple questions before I hand the microphone back over to Aydin.
Questions? Are you hiring interns?
Oh yeah, we are indeed looking to expand. In fact, this event is not specifically targeted at hiring. It's more just to kind of hang out and chat about deep learning, but we're organizing a deep learning dinner in Berkeley in May. And we're going to spend a lot of time chatting about sort of applications of parallelism in deep learning. And we're still figuring out the details, but please do send me an email if you're interested at forrest@deepscale.ai, and use the subject line Berkeley Deep Learning Dinner so it doesn't get lost in my inbox. And I believe these slides will be up on the Great. So on the website, so that you can find this information later on.
Okay. Only the guest lecturers get the claps. That's the rule. What was it? I mean, I don't like companies. I just have contacts with them. And I'm not going to endorse any company because I don't know their internals. In fact, even if I did, probably there's an NDA when I talk to them. So I can't even tell you that. But for example, this was the joke at the put it on the right, the NIPS workshop. That so this visualization is some sort of AlexNet, I think. And this company, GraphCore, makes these visualizations. The CEO was giving a talk at one of the NIPS workshops, and his joke was, well, right now we're known as the company that makes beautiful neural network visualizations. Hopefully next year we'll be known as the company that makes great hardware for neural networks training and inference. I have colleagues that I respect that are in Cerebras. If you want to go intern, they were looking for some, send me an email, I'll put them in contact with you. And vice versa, whichever way direction. But again, either I don't know their work, or even if I did, I can't talk about it. So what else? Okay, not exactly what I wanted to show, but let's come back to the rest of the ML lecture. So everyone is sufficiently satisfied with neural networks. Let's try some no longer hot, but these things are cyclical topic. Called, well, support vector. So this is where the slides go. So we'll go a little bit about support vector machines in the next 20 minutes. We have, one thing I also wanted to mention is there is a list of project ideas that's somewhere in the both the website. There's a project tab, and so one recent work on that area that's not been highlighted. Some of these are already highlighted in that project ideas. Are the lower bounds work by Jim, one of the instructors of the class, and one of his students. Where what they did was they showed that there's multiple different lower bounds that apply to convolutional neural network training, and they kind of look for demonstration in practice that these lower bounds are achievable. So if you want to work on that, that's also a cool project idea. You can find it in the projects list. So what's the support vector machine? It's really, it's a theory that's been developed, I think in the 90s by this guy called Vladimir Vapnik, which is pretty cool and deep. But at the end of the day, it's based on the approach that you're trying to find a hyperplane that separates your data, right? And you're trying to maximize the margin between those pieces. So that's that creates naturally an optimization problem. You're trying to maximize the margin between these two areas, and these things are called considered support vectors. These little these W's. Right, so you're trying to find the two support vectors that are as far as possible in the margin-wise, and if you look at the optimization problem, you're dealing with a constrained quadratic optimization problem. So this is, you can solve it directly. You can give it to your typical optimization solver. But just like I said in the beginning of the machine learning, the first part of the lectures, there are usually specialized solvers for pretty much every machine learning task. And in this case, there is a specialized solver called sequential minimal optimization, and we'll talk about it, what it is. It's really solving the QP problem using a strangely effective heuristic. But it has parallelism issues. So what's the main idea in support vector machines and a lot of kernel machines is your input space will not be like this in general, right? It's not going to be linearly separable. We know this for a fact. So, but what they rely on is there is some transformation that takes your input space from its natural dimension to some higher dimension, and in that space they'll be separable. That's the main idea, and once you do that, you can find a hyperplane in that. And of course, these are only two-dimensional examples, but I'll show you one higher dimension. And so, how do you do that is going to be the topic of deep papers, but in general, there are like 4 or 5 kernel functions that seem to work in a lot of applications. And the recommendation, if you go to the most popular software in support vector machines, it will say, first try the whatever radial basis function, the kernel function. If that doesn't work, you use the next one. And eventually, one of them will actually give you a good training and tester, and you're done. So here's the example. That's from still old, but I think very accessible book of the modern AI. I think Russell and Norwick's book. So if your space is like a sphere, if the black dots are like a sphere, and then every white dot is outside the sphere, and you're trying to classify them, it looks like really hard to map this thing to a higher dimensional space that will be linearly separable. But it turns out it's not that hard. If you just use this transformation, it'll get you this 3-dimensional space, and they'll be separable by a plane there. So then your kernel function that maps your 2-dimensional space to a 3-dimensional space is this, the square of the first vectors, the square of the second vector, and the square root of 2 times those 2 vectors. That will work. So that's your kernel function, right? But the challenge here is you don't want to map your input space to a higher dimensional space. That's even bloating your data, right? You're not only processing your whole data, you're potentially actually increasing the size of your data, because the dimension can be from 2 to 3 instead of 2 to 3. You might need to do it even higher mapping, higher level mapping, and increase your storage. So how can you avoid it is most of these kernel functions do not need to be explicitly computed and their results to be stored on the data. You can apply it as you go, and that's so-called the kernel trick, right? So, and why does this work? You can think of it, you have 2 points, well, you apply one kernel function, and then for the second vector, you also apply it. This needs to be j, apologies. And the result is the same thing as if you actually just, applied it on the result, as opposed to first applying the kernel function and multiplying them. You can just basically multiply them and apply the kernel function. The result is the same. Most of these kernel functions are chosen so that they have this property, and that's how you get around it. But we haven't yet come to parallelism. I know these are mostly theory. So that's the motivation behind the kernel trick, why you don't want to do that. Takes an extra amount of memory, lots of operations. And so the algorithm that is used in sort of quadratic programming is called sequential minimal optimization. And I think it's best described in this figure. So when you open up this long optimization function, this is what you get. And so this is a constrained optimization problem where there are a bunch of equality constraints. So the sum of all the Lagrange multipliers and for all the samples needs to be 0. So think of this as your support vectors, and these alphas, the Lagrange multipliers, are how active those support vectors are. If a support vector is not active, that data is irrelevant for the boundary decision for separation. If it's active, there will be a non-zero value, right? I think if you take optimization classes, you will probably remember how these things relate to each other. So the sequential minimal optimization's main idea is, how can I perturb the Lagrange multipliers as minimally as possible? So, at any point, if I'm trying to keep this problem feasible, if I'm coming up with an algorithm that's primal feasible, if I change one of the multipliers, then this equation will no longer hold, right? Assuming it held before. So basically, I need to change at least 2 of them at once, so that the equality constraint that used to hold still holds. There's no way I can change one variable unless it's y is 0 and still hope that the equation is going to hold. So that's what sequential minimal optimization does. Just choose 2 Lagrange multipliers and just change their values. If you increase one of them, you have to decrease the other one proportionally. Not exactly that way. Depends on what yi is. And just continue until convergence. And this is an extreme push of an idea called chunking. So instead of looking at all the Lagrange multipliers all at once, you basically are looking at a subset of them, and this sequential minimal optimization just takes that idea to the extreme. What is the minimal amount of things that I can optimize at once? I think all I said. And the way you choose those is a heuristic of the algorithm, and I'm not going to go into detail. But here's the problem. If you're only changing 2 things at a time, then you don't have a lot of work. In a sequential implementation, this is a great algorithm, but there is not much parallelism in there. Like, how are you going to do when you're only changing 2 variables at a time? And you just basically look at how these things relates. The number of iterations of the algorithm is pretty much on the same order as your data size, number of samples. And there's not much parallelism you can do by individually parallelizing these single iterations. Like I said, the implicit parallelism here is not going to work because not enough work exists at each iteration. So what did people do? This is actually a paper by Watnick himself, written in Microsoft Word. It's really hard to read the formulas. So what does it do? You divide your data into pieces. In this example, it's 8 pieces. And you train as you try to find the data points that have Lagrange multipliers 0, that are no longer support vectors. So you only pass the support vectors to the next layer, and you retrain it. You only pass the support vectors to the next layer, and eventually you will get to some global support vectors. If you're not satisfied with the result because this is not doing the same thing as a global optimization does, you can just go back and retrain it using the warm start of the previous Lagrange multipliers you have used. So that's one of the important parts. You basically, every time you go to the next layer in this cascade, you pass the Lagrange multipliers so that you don't restart the training from scratch. You just keep improving on it as a warm start. Seems to sometimes work in practice, but there are some issues we'll see. So this has been, a different approach has been tried. Instead of passing just the support vectors, this approach, divide and conquer SVM, actually passes all of the data to the next layer, right? So, and there are some theorems to explain why this might actually work. I want to say in the previous slide that the original partitioning of the data is random here. So you just basically say the first processor will get 1/8 of the data, and I don't know what's in that 1/8 of the data. But here, you do something a little bit more meaningful. You basically cluster your data using kernel k-means and use that initial partitioning to train each one of the support vector machines. And then there's like a similar tree-like pattern where you try to merge these support vector machines. But instead of just passing vectors, you pass all of the data. And there are some theorems that you say, like the local support vectors will be close to the global ones under certain assumptions. That's most of the papers in the area, right? And it doesn't take too long for someone like Yang to understand that you can actually combine these two ideas, where the downside of this approach, the original approach, is the load balance, among other things. And the downside of this approach is really you're passing all of the data that creates a lot of communication, 2 layers. So basically you can do 2 things that were good about them, like use kernel k-means to divide the data set in a more principled way, and just pass the support vectors as opposed to the whole data. And you see one issue here. So what's happening, this is, I'm going to go a little outside the forest's story. There's one issue with reduction trees, is there's more work is done eventually in fewer and fewer processors at the next layer. And here's what's actually happening, very similar. At first there's like 8 processors working on the problem, so it takes 5.5 seconds. Then the problem is getting smaller, but the number of processors go down significantly faster than that. And somewhere towards the bottom layer, there's only one processor working on all of it, and it takes even longer than the first layer. So this is not exactly what you want. So the tree-like structure has this problem, and how can we avoid it is, well, we will never do this tree-like merging. We will just partition the data, everyone will process their SVMs, and there will be a single reduction. Looks like a very simple idea. And why would this ever even be correct, right? Because the tree-like reduction does multiple levels of correction. By combining them in a binary tree fashion, you're basically trying to recover the correct global support vectors. A single merge might not do that. And I think the idea comes from, according to the paper, the idea is based on how the kernel k-means cluster the data. If you think about one very popular kernel, which is this exponential thing, Gaussian kernel, if there are 2 data points, their kernel distance is very small, because if they're far away, this is e to their distance, a to the minus their distance squared. So very quickly, those distances go down much faster than the original data set. So what does this tell us? If I partition my data set using this algorithm, the support vectors of one data set will be almost irrelevant to the other pieces of the data set, the other, let's say, 7 data sets. Because if they were close to each other, they would be clustered together. Since they are clustered separately, they probably will not have an effect to each other. So that's the basic idea. And it seems to work fine. It fixes the performance except for load balance. So you see there's some machines that take much longer than the other machines. And the solution is there. Instead of using blindly the k-means, you use some k-means approximation that also considers the load balance. But now you can't just come up with an algorithm that completely ignores load balance, k-means, because our whole assumption was that the k-means will guarantee that the support vectors of one subset of the data is irrelevant for the other subsets. So you're basically only augmenting the k-means result slightly to get load balance. And in the end, it seems to work much better and gets reasonably good accuracy, almost as good as distributed sequential minimal optimization in many cases, and it takes much less time. I think I'm actually only going to talk all this. There's 5 minutes left, but I have no intention to move to the next lecture. You can use this to ask me or Forrest questions. Or, oh, one more thing. Class projects. So I'm holding office hours tomorrow and next week. Last year, a lot of people came. I also held 3 iterations of this last year. And the number of people that came kept increasing. And then in the last one, there's more people than the 2-hour slot allows. So they don't get the time to talk about their project ideas. So don't leave it to the last one of those office hours. That's right before the spring break. There might be more students than my time allows. So if you can come tomorrow, that'll be better. Any questions about also projects and homeworks? That's like you haven't asked in Piazza? Or is there some question that's in Piazza that you haven't gotten a response yet? Okay, everything looks good. All right.